Okay, welcome guys to the new lecture of our Mechanics of Solids 1, which is about deflection of beams. In this video, we will discuss the method for determining the deflection and slope of the beams. The analytical method, that is known as the double integration method, will be used along with the discontinuity functions, and we will solve some statically determinate beams, and at the end of the video we will use these methods to solve for the support reactions on a beam that is statically indeterminate. So let's begin with the chapter or this concept. Now before understanding the deflection, you need to know about the elastic curve. That what is elastic curve? As you know that the deflection of a beam or shaft must often be limited in order to provide stability and for beams to prevent the cracking of any attached brittle material such as concrete or plaster, right? So it is very important that the deflection of the beam must be limited so that to overcome the instability for beams. Alright, most importantly, through slopes, those slopes and displacement must be determined in order to find the reactions if the beam is statically indeterminate, right? So as you already know that what is statically determinate and indeterminate. So in the case of statically indeterminate beams, the slope and displacement must be determined to find the reactions in the beam. Alright, in this lecture we will find these slopes and displacements caused by the effects of bending. So before finding the slope or displacement, now what is slope and what is displacement? It is often helpful to sketch the deflected shape of the beam, which is represented by its elastic curve. So first of all, you need to understand the deflected shape of the beam, that what will happen to a beam if a certain kind of load is applied on it, given that the boundary conditions which we are known as the support conditions, right? With specific support conditions under given loading, how the beam will deflect, right? And it is done by its elastic curve. So that deflected shape is called the elastic curve. This curve passes through the centroid of each cross section of the beam, and for most cases it can be sketched without much difficulty. So elastic curve is basically representing the longitudinal center line of the beam. Now here is an example of a simply supported beam. You can see that a simply supported beam where a hinge support and roller support are there, and a point load has been applied to its center. So the beam deflects in this way, right? Now if you just change the support conditions, you can see that the length of the beam is same, the load is same, but you have just changed the support conditions and made both the supports as fixed. Now just look at the deflected shape. Here the deflection starts right from the support, right, on both sides, but here you can see that it goes horizontally straight because of this fixed support. It does not allow rotation as well as displacement. So this one goes straight, and the deflection is started as you can see right from the here, right? And this deflected shape ends here, and where it is going to get horizontally straight. So for the beam to fully understand its deflected shape, you must know the effect of the support conditions, you must know the effect of its length, you must know the effect of the loads on it, right? And you must also know its flexural stiffness. Now here is another example of the cantilever beam. You can see that the beam is fixed at this side and it is free on the other side. There is no other support and a point load, a same point load, and please keep in mind that I have kept the length same. Okay, the same length has been subjected with different boundary conditions. So this load is applied again at the middle, and you can see the because of this fixed support the beam is initially horizontal and then it gets deflected, right? And after this point, since there is no load, it goes straight. So the deflection is minimum as we compare to this case, where the same length of beam with the same support condition with the same quantity of load, but just applied at the edge. So the deflection increases just by changing its position. right? So it was just for you people to understand that how the deflection and the slope changes if we only change the location of the applied load, right? So it says that when doing so, just remember that supports that resist a force such as a pin, we call it as a hinge support also. So the pin support only restrict the displacement, right? And those that resist a movement, for example a fixed wall, restrict rotation or slope as well as displacement. So if you consider this beam, it is usually called as propped cantilever beam, whose one end is fixed and the other end is hinged or pinned, right? So the fixed end doesn't allow any rotation or any displacement, and the hinge end doesn't allow any displacement. See, the beam is not moving up or down, but it does allow the rotation of the beam. So this is the main difference. You need to understand that why support conditions affect the elastic curve or the deflection of the beam. So two examples of the elastic curve for loaded beam are shown in figure 1. This is your figure 1. I have explained this one, and this is an example of the overhanging beam where this one is the pin support or the hinge support and this one is the roller support. The load is applied at the free end and you can see the deformed shape of this beam. So if the elastic curve for a beam seems difficult to establish, it is suggested that the moment diagram for the beam be drawn first. So you can also get an idea for the elastic curve from the bending moment diagram, right? Using the beam sign convention established previously, we already understand from the previous concepts that this sign, when the moments cause the beam to bend in concave upward, then it is a positive bending moment, right? And when it cause the beam to bend in a concave downward, then it is the negative moment. So these m's are minus and these m's are plus. So again, I have drawn that propped cantilever beam. See, this is the propped cantilever beam, and I have modeled it, and you can see that by making this support, the far support, as a hinge support or roller support doesn't make any difference, and the deflected shape is similar to what you have seen here. So initially it is straight and the beam is bent, or the slope is there at the far end, because this support does not restrict the rotation or slope, right? Again, you have seen the overhanging beam in here, right? So I have modeled that as well, and the load is also applied. Yeah, this figure is similar to the one presented here, right? And you can see the deflected shape is also the same, right? But what if I just change the location of this load, and for instance I have made this load at the middle of this span, and I have removed load from the free end. So just look how the elastic curve will be. So the deflection just changes oppositely, right? Here the deflection was upward in the first case, and here the deflection is downward. So it means that in this case the bottom fibers are in compression and the top fibers are in tension, but it is opposite here where the bottom fibers are in tension and the top fibers are in compression. So this is how just the location of the load changes the behavior of the beam, right? Therefore, if the moment diagram is known, it will be easy to construct the elastic curve. For example, this beam, this is again an overhanging beam. Two point loads are applied, one at the free end and one at the middle of this between these supports B and D, right? Now what is C? C, for example, if you draw the bending moment diagram, for example, first you need to draw the shear force diagram, then you need to draw the bending moment diagram, which will be like this. And this C is the point where the which you called at the inflection point, right? Where the bending moment diagram is converting from negative to positive, changing from negative to positive. This is of very importance, this point, right? And Due to the roller and pin support, the displacements at B and D must be 0. So as we know that the roller support as well as the pin support doesn't allow displacement in the vertical direction, so the displacements must be 0. Zero deflection should be at supports B and D, right? Within the region of negative moment, this is the region of negative moment from A to C. This is the moment region of negative moment. So in this region the beam will deflect a concave downward. If you remember this slide, see, in the region of negative moment the beam will bend in the concave downward. So in this region its direction will be as a concave downward. However, after this point of inflection it will be concave upward. See, so from the bending moment diagram you can easily understand the direction of this elastic curve or the deflection diagram. So it should be noted that the displacements delta A and delta E are specially critical. The displacement or the deflection of this A point and the E point are very critical and need to be found. At point E, the slope of the elastic curve is 0. Here the slope of elastic curve is 0, and there the beam's deflection may be a maximum, right? So here the deflection is maximum in this span. Whether delta E is actually greater than delta A depends on the relative magnitude of P1 and P2 and the location of the roller at P. So if delta A will be greater than delta E or not, so it only depends upon the magnitude of these forces, right? The same beam is shown here, which is modeled, and the deflected shape is presented. Following these same principles, note how the elastic curve in figure 4 was constructed. This is your figure 4, right? Here the beam is cantilevered from a fixed support A. This is your support A. The beam is cantilevered and point load P is applied at somewhere middle of the beam, and a unit moment is applied at the free end, right? So the largest displacement will occur either at D or where the slope is 0, or at C. So this is your D and this is your C, because when you draw your elastic curve, so this is fixed support, it will be initially straight, right? And after some distance it will get starting moving downward. So this is your point of inflection, right, where the bending moment is changing from negative to positive. So for positive moment, see, till negative moment it is concave downward, right? And after this point it looks like it is concave upward, right? Now what will be the position of C? Either it will be below this line or initial line, or it will above. Of course it depends upon the magnitude of M, the relative magnitude of P, the position of the P, and many other aspects. So I have modeled this as well. So you can see that this is your fixed support, this is the applied moment at this far end or the free end, and this is the applied load vertical direction. So this is the elastic curve, and let me show you that you can change it. For example, this is the elastic curve that I just showed you. So what happened if I just change the magnitude of the bending moment at this end? So let's see what happens. So I will select this joint, right, and I will go to the loads and I change it to the okay, let me show you first that what is the current value. So the current loading at this joint is 70 kPa, right? The units are in kPa and the magnitude is 70. So what if I make it just let's say 50? Okay, so assign joint loads and I will make it 50, and I will make it replace the existing load, right? So the 70 will be replaced. So just for confirmation, see, it is now 50. Okay, and I will run the analysis and we will see that how does it deforms just by changing the bending moment value at the free end, right? Please keep in mind that the vertical force is same. So you just saw that the elastic curve has been changed. How it was here, it was going above the original line, right? And now what happens to it now? It is somewhere down. It is getting upward. See, it is not going further down, it is going upward, but it is not crossing that line. Okay, so let's play again with it and make it what would you say, 60. So previously it was 70, then we made it 50, now it is 60, and run the analysis and see what happens. So it will deflect, and you will see that how the deflected shape changes, or the elastic curve changes. See, it is very close to this end right now. So the value of this elastic curve or the deflected shape, the shape is changing by just changing the value of the moment. Let me show you about the, for example, what is the load applied to it. See, a point load at the middle of the beam is applied, and at this point we are just playing with the moment. So now I am making it 65, and what happens when I run the analysis? So you will see that it will be almost crossing this line, right? So this is what I wanted to make you people know, that how just changing one parameter caused the change in the elastic curve, right? So similarly you can see that in this software I have modeled cantilever beam, where you can see the deflection in the beam, right? So if you check the values, the dark red is zero deflection, and the light blue is the maximum deflection. So for the cantilever beam, this the deflection at the fixed end is 0, and as you move away from the support, the deflection is increasing. See, for example, the light green is -7 power -2, and the light blue is minus 1.2 power -1. So the deflection is increasing, right? Likewise, if you check for the another beam which is simply supported, and I just want to make you visualize that how it will look like. So let me make it convenient for you. So this is how the simply supported beam gets deflected. You can see the maximum deflection is happening at the middle, and the zero deflection or displacement is happening at the supports, because the roller and hinge support doesn't allow any displacement in the vertical direction. The beam is rotating here as well. See, here you can visualize very beautifully in a 3D. See, so I was just wanted to make you visualize in a better way. So this is how things works. So let's get back to our lecture, which is about the deflection. So the next thing, after realizing the deflected shape or the elastic curve, the next important thing is the moment curvature relationship. It is very important topic. Before we can obtain the slope and deflection at any point on the elastic curve, it is first necessary to relate the internal moment to the radius of curvature rho, okay, of the elastic curve. So once you know, for example, let me take you to this beam in figure 5a. This is a beam, right? And in this beam you just see that there are different loads acting on this beam: point load and UDL and moment. So due to that, the beam has been deflected in this way, right? So the curvature, for example, this is the cross section, the same cross section dx before deformation, right? And this is the same section after deformation. So there is a curvature, right? Because Due to this bending, the bottom fibers are elongated and the top fibers are shortened. So this length is definitely less than this length, and this length is definitely greater than this length, but the dx which is at the neutral axis will remain same. So this is your curvature and this is your radius rho. I just wanted to make you know that what is rho. To do this, we will consider the beam shown in figure 5a as I presented to you, right? The localized y coordinate is measured from the elastic curve's neutral axis to the fiber in the beam that has an original length of ds is equal to dx, as I show you that this dx is the neutral axis and this is a line that we are assuming. Now consider this line, initially its length is equal to dx, right, because it is undeformed, and the distance between dx and ds is y. So ds lies at a perpendicular distance y from the dx, right, and after deformation it is modified into ds prime. See, this is ds prime. So as it is above neutral axis, so ds dash should definitely be less than ds. In flexural stress formula, we developed a relationship between the normal strain in this fiber and the internal moment and radius of curvature of the beam element. So it is 1 by rho is equal to minus epsilon by rho, and for convenience of you people I have presented it here. It says that the axial strain is equal to this ds dash. Okay, I have taken this from the chapter of the flexural formula. So in that formula they are putting it as a delta and here they are putting it as a d, okay, but there is no difference. So it says that ds dash delta s dash minus delta s divided by delta s, which is strain is equal to change in length divided by original length. So what is change in length? This final length minus this original length. So ds dash minus ds, right, divided by the original length, and making it the limit is up, it is approaching 0, right. So this is your very easy formula for the normal strain or the axial strain. Now you know that ds is equal to dx. See here, ds is equal to dx and dx is equal to ds is equal to rho into d theta. See, this is your dx, which is length of the curve, this is your radius of the curve, and this is your theta. So it is a very simple formula that length of the curve is equal to radius times the internal angle. So rho into d theta is your length of the curve, which is ds or dx. Now what is ds dash? So ds dash is also making the same angle, but its distance is different. What is its distance? Its distance is this rho, which is from here minus y. So rho minus y is its length. So rho minus y into d theta. So now we know the values for ds, the ds dash, and we can put in this equation, which is ds dash, which is now rho minus y into d theta, c, minus ds, which is rho d theta, divided by ds, which is rho d theta. So we can take d theta as a common and it will get cancelled, and we will solve it rho minus y minus rho. So rho will get cancelled with this rho, so we will only be left with minus y by rho. So epsilon is equal to minus y by rho, and if you took y to the other side of the equation, so it will be this equation, 1 by rho is equal to minus epsilon by y, right. So I hope you understood the thing which I wanted to make you understand. Now since Hooke's law applies, so your strain is equal to stress divided by elastic modulus, and your flexural stress is equal to my by I. Now why I am putting minus? Because we are talking about the compression side, right. After substituting into the above equation the values of epsilon, for example, if you put epsilon in it, that will be 1 by rho will be equal to sigma by ey, and when you put the value of sigma, so it will be equal to my divided by eiy. So y will get cancelled with this y, and we will be only left with m over ei. So this is another important equation, equation 2. So 1 by rho is equal to m by ei. These are different terminologies that I already explained. The sign for rho therefore depends on the direction of the movement, as we understood, as shown in figure 6. This is your figure 6. when m is positive, rho extends above the beam. So here m is positive, right? So rho will be above the beam, and when m is negative, the rho extends below the beam, right? So the sign for rho depends upon